Hello and welcome to educator.com and welcome to the first lesson of biochemistry. So biochemistry is absolutely an extraordinary class. There's a lot of information and all of the information is absolutely exciting. So before we actually jump into the biochemistry with proteins and lipids and carbohydrates and metabolism, what we want to do is do just a little bit of a general chemistry review, all of the things that are going to be very important. Now you've seen most of these things before, but it may have been a while since you actually worked with them. So for the first couple of lessons, we're just going to do a nice chemistry review just to get everything going again, and then we'll jump into the biochemistry. So let's get started, and welcome again. Okay, so we're going to start off by discussing aqueous solutions and the notion of concentration. So an aqueous solution, the reason we're discussing this is because the body, all of the chemistry that takes place in the body takes place in an aqueous solution, in water. We're mostly just water, and it's just a whole bunch of molecules that are dissolved in that water, running into each other, doing the things that they do. So because this is biochemistry, the chemistry of biological systems, the chemistry of biological molecules, all of the chemistry that takes place, the chemistry that you learned in general chemistry regarding aqueous solutions, all of it absolutely applies here. So let's go ahead and start with our definition of solution, and we'll work our way forward. So solution. So a solution is just a solute dissolved in a solvent. Dissolved in a solvent. So there are two things. You have the solvent, and then you have the solute, the thing that's actually dissolved in it. For biochemistry, it works out really great because the only solvent that we're concerned with is water, thus aqueous. You remember from organic chemistry, you're going to have, all kinds of solvents. You can have hexane, you can have ethyl acetate, you can have all kinds of things, alcohol, but for biochemistry, it's water, so it makes our life that much simpler. So some examples of solutions. Let's see what we've got. So we have sugar dissolved in water. That's a sugar solution. Sugar dissolved in water. So the sugar is the solute. And sure enough, the water is the solvent. H2O is the solvent. In this particular case, you have a solid, the sugar crystals, and the solvent happens to be a liquid. Now, it doesn't have to be this way. A solute does not have to be, a solid, and a solvent doesn't have to be a liquid. It just turns out that way most of the time, and certainly in our case. Let's see, how about another example? Let's take salt dissolved in water. So a salt solution. So a salt. When a salt is dissolved in water, again, the salt is your solute, and H2O is again the solvent. Oops, not solute. What we have is solvent. Okay. Now, as I said before, a solute does not have to be a solid. So, a solute does not have to be a solid. It just happens to be most of our experience from general chemistry, organic chemistry, and just normal day-to-day stuff. Most solutes happen to be solid because we dissolve them in something. We see the crystals just sort of disappear as the solution is created, but it doesn't have to be that way. And in fact, we have a daily example of that, carbonated water. Carbonated water, or soda, is actually just CO2 gas dissolved in water. So a solute is a gas. So let me write this out. Carbonated water. Water. In this particular case, the CO2 is the solute. It is a gas. And H2O is the solvent. H2O is the solvent. Now, in this particular case, in order to make sure that the CO2 actually stays dissolved in the water, to create the carbonic acid solution, the the carbon dioxide solution, we have to put it under pressure, which is why when you pop the can, the carbon dioxide escapes, and that's the bubbles rising. Okay. Now, the solvent itself, the solvent does not have to be a liquid. It does not have to be a liquid. So this notion of a solution is actually a very, very broad definition. It's when something is dissolved in another. In other words, when you get what looks like a completely homogeneous thing where you can't see the individual particles of the solute and the solvent. It just looks like one thing. So the solvent does not have to be a liquid. But for us, we don't have to worry about that. Our solvent is water. Okay. So let's see what we've got here. Okay, so sugar and salt, they both dissolve in water, but do they dissolve the same way? You know, sugar crystals, salt crystals, when you're a kid, it looks like they behave the same way. It isn't until you actually get to chemistry that you discover that the dissolving process is actually completely different. And what's going on inside the solution, the chemistry, is entirely different. So let's write that out. So sugar and salt both dissolve the same way. But do they, well, actually, they don't dissolve the same way. They dissolve. The question is, do they dissolve the same way? Sorry about that. Both dissolve. But do they do so the same way? And the answer is no, they do not. Now, covalent compounds. So covalent compounds, basically compounds that are made of non-metal bonds, sharing of electrons. Covalent compounds, they dissolve. When they do so, we say that they dissolve. The example of that is sugar. Sugar is a covalent compound. Even though it has some hydroxy groups where some of the H's can actually be removed, it's actually considered a covalent compound because you have carbons bonded to other carbons, you have carbons bonded to oxygens, you have oxygens bonded to hydrogens. These are single bonds, single and double bonds. So when these dissolve, they just dissolve. Now salts, or ionic compounds, I'll write them as ionic compounds. And of course, the word salt is a generic term for any ionic compound. So I'll put salts in parentheses. Now, when salts dissolve, when these dissolve, because not all salts dissolve. You remember when you were doing solubility product, if you take like sodium chloride, which is normal table salt, put it in water, yes, it'll dissolve up to a certain point. If you put silver chloride into water, it'll just sink to the bottom. Remember precipitation? Precipitation is salts that don't dissolve in water. Now, salts, when they do dissolve, they dissociate. This is very, very important. They dissociate. In other words, dissociation means they separate into individual ions, into individual free ions. This is very, very important. So in a covalent compound, you can put it in there and you're not creating an electrically conductive solution. But when salt dissolves, like sodium chloride, it breaks up into sodium plus and chloride minus ions floating around. Well, now this solution actually will conduct electricity because you have positive and negative charges floating around. So the chemistry, the behavior of the solution is entirely different, even though they actually look the same. That's what's important. Okay, so let's just take table sugar. Let's just sort of see what this looks like. So C12H22O11, this is sucrose. As a solid, when we dissolve it in water, what we end up with is C12H22O11 aqueous. So this AQ tells us that it is dissolved. This is solid, drop it in water, it is dissolved. Okay? That's what this AQ means. Let me go ahead and write that. Okay. Means dissolved. It means that it is surrounded, each individual molecule of sucrose has separated from the crystal and is now surrounded by a bunch of water molecules, which is why you can't see the individual crystals in the water anymore. It is now a sugar solution, not a sugar crystal. Okay, notice one molecule of sugar produces one molecule of aqueous sugar. 1 mole of sugar 1 mole of a sugar crystals will produce 1 mole of free individual particles. These particles right here, this aqueous, that means these individual sugar molecules are floating around freely as molecules. Nothing has come apart. The carbon, hydrogen, oxygen bonds have not broken. It's just the whole molecule just floating around freely, whereas here, each molecule is arranged in a crystal. Now, let's go ahead and take something like magnesium chloride, a salt. So, magnesium chloride, an ionic compound, this is a solid. When I drop this in water, what happens is it dissociates. It completely comes apart into its free ions. It separates into a magnesium 2+ ion floating around, and you have 2 chloride ions floating around. So what happens is 1 unit of these, we don't speak about ionic compounds as molecules because this is not really a covalent bond. This is a positive charge and a negative charge. They stuck together. It's a very strong bond, but it's not covalent, so we don't talk about it as a molecule. You can call it a unit. I mean, it's not going to be the end of the world if you call it a molecule, but just to let you know. So 1 unit of magnesium chloride produces 3 particles, 1 magnesium ion particle and 2 chloride ion particles. This is very, very important, as you'll see in a minute. So let's go ahead and put AQ and AQ. In general, when you have ions on the right side of the arrow in an equation, the presumption is that they are aqueous, that they're dissolved, unless you're specifically speaking about the gaseous phase, but we're not. Everything is aqueous chemistry for us, so we don't need to put the AQ, but I'll put them here. However, in the future, I will not. Okay, so notice 1 unit of MgCl2, of the magnesium chloride, it produces 3 free particles. That's it. That's what's going on here. 3 free particles floating around in solution. Floating around in solution. So covalent compounds dissolve. Salts, when they do dissolve, they're actually dissociating. Okay. So now let's talk about the notion of concentration. So if I take 1 gram of salt and I drop it into 100 milliliters of water, versus if I take 20 grams of salt and I drop it into 100 milliliters of water, clearly there's going to be a hell of a lot more salt. The concentration of the solution is going to be larger in the second one. There's more salt in it. The volume of the solution is the same. It still stays 100 milliliters, but I have 1 gram in one, 20 grams in the other. I need a numerical method for differentiating between the two. We call that concentration. So concentration, there's a whole bunch of ways to express concentration. We're going to be concerned with 2 of them, molarity and percent by mass. Those are the ones that I'm actually going to introduce and do examples with. However, for the most part, we're really only going to be concerned with molarity, moles of solute per liters of total solution. Okay, so expressing concentration. Let me go ahead and put a little line here. Expressing concentration. Okay, so the first way, and the primary way, is something called molarity, and it is expressed with a capital M. Okay, molarity is defined as the moles of solute divided by the liters of solution. Liters of solution. So this is the final volume. Now you remember I said that a solute doesn't have to be a solid. If I take a liquid solute, like liquid glucose, and I drop it into liquid water, well, if I take 10 milliliters of the liquid glucose and put it into 100 milliliters of liquid water, now the total volume of my solution is 110 milliliters. It's not 100 milliliters. So volume, molecules take up volume. So this is liters of total solution. This is just moles of solute, the things that you add. It's very, very important to keep these things straight. Okay, so let's do an example with molarity. Again, It's all about the examples. It's all about working with these things, using your intuition, everything that you already know from previous classes. So we have 7 milliliters of lactic acid is dissolved in 130 milliliters of H2O. What is the molarity of the lactic acid? What is the molarity of this lactic acid solution? Okay. Well, let's write our definition. So the molarity is going to equal the moles of lactic acid divided by the liters of solution. Liters of solution. So that's what we need. We need this number, the moles of lactic acid. We need the liters of solution, and then we're going to do the division, and that'll give us our concentration in moles per liter. That's the unit, moles per liter. So let me write that here. Moles per liter, and it's symbolized with a capital M. I prefer to see my entire unit. This M thing is always, it hasn't confused me, but I like to work with my entire units. I don't like anything to be hidden, but that's just a personal preference. Okay, so before I do that, this is biochemistry, and our examples, we're going to try our best to use as many biological molecules as possible. So as we do that, I'm going to just draw out the structures of these things just so you get accustomed to seeing them. And that's how we develop a sense of familiarity with these biomolecules, and they are going to get larger and larger and larger. So lactic acid looks like this. I'm going to do a straight carbon structure. H and CH3, and we have an OH there. So we have 3 carbons. We have a carbonyl group. This is a carboxylic acid group. This is an alpha hydroxy acid, actually, and it's an alpha hydroxy acid. Remember, this carbonyl carbon, this is the carbonyl carbon right here, the one that's attached to the double bond. Let me do this in red. That is the carbonyl carbon. This is called the alpha carbon, and this is called a hydroxy group. So this is called an alpha hydroxy acid, an alpha hydroxy carboxylic acid, 3 carbons long. This is lactic acid. This is what develops in your muscles when you start to get sore, when you exercise really, really fast, and the body starts to metabolize under anaerobic conditions without oxygen. The byproduct is actually lactic acid. That's what you feel when your muscles start to get really, really sore when you're exercising really, really fast. Okay. Now let me see, what were we doing? We want the molarity of this lactic acid solution. Okay, so I'm going to keep it in red. So let's do moles of, so we need the moles of lactic acid. Well, we have the milliliters of lactic acid. That's what they give us. We want the moles of lactic acid. How can I go from milliliters to moles? Well, I know that I can go from grams of lactic acid to moles via the molar mass, and I could go from milliliters to grams via the density. So that's my solution path. From milliliters, I'm going to go to grams, and then from grams, I'm going to go to moles. This is density, and this is molar mass. Okay, so now I look up the molar mass for lactic acid, I look up the density for lactic acid if they don't give it to me in the problem, and there's no guarantee that you're going to be given to it in the problem. Part of the idea is to use your resources, whether they be computer resources or book resources, to find the things that you need. It's really, really important to be able to do that. There are tables, and it's very important that you become adept at utilizing your resources, because there's no guarantee. In real life, you're just going to be presented with a problem. You have to look up these things. So when we look things up, the density of lactic acid is 1.209 grams per milliliter. And of course, I hope you will confirm this for me, because I could have read it wrong myself. And the molar mass of lactic acid is 90.08 grams per mole. So we have 7 milliliters of lactic acid times 1.209 grams per milliliter times 1 mole happens to be 90.08 grams. And now, of course, gram cancels gram, milliliter cancels milliliter, and what we're left with is 0.0939 moles of lactic acid. You know what? I'm going to write this out. I'm just going to, moles of lactic. I'm just going to put lactic. Okay, so now we have the number of moles. We have the numerator. We have that. Now we need the liters of solution. Liters of solution. Okay. Well, this one is really easy. We had 7 milliliters of lactic acid. We have 130 milliliters of H2O. Well, both of them were liquid. Remember what we said? Liquid solute, liquid solvent. Just add the liquids. The total volume of the solution is going to be 137 milliliters, which is equivalent to 0.137 liters. Because again, liters, moles per liter, that's the definition. Okay, now let's just go ahead and solve the problem. I'll do it on the next page here. So, molarity, the concentration is equal to 0.0939 moles of lactic acid divided by 0.137 liters, 137 milliliters. What you get is 0.686 moles per liter, or 0.686 capital M, molarity. There you go. Either one is absolutely fine. So that's our concentration in moles per liter. In this particular situation, in 1 liter of solution, you have 0.686 moles. Okay. So now let's introduce another expression, another way of expressing concentration, and this is percent by mass. This is also very, very popular. You'll see this a lot on bottles at the grocery store and stuff. They're expressed in terms of mass. So let me go back to black here. So another way to express concentration is, I don't need that, is percent by mass. Percent by mass. Okay. Now, percent by mass, you'll see it this way. Percent M divided by M. Percent MM. That's what this is a symbol for percent by mass. The definition is this. It's the mass of the solute like any percent, it's always the part over the whole times 100. It's the fraction times 100. That's what a percent is. A percent is just a fraction that has turned into a number that's a little easier to handle. That's the only reason the percent exists. You actually don't really need that whole multiplying by 100. I mean, you know, the decimal is just fine, but I guess some people just prefer numbers that are not pure decimals. Okay, mass of solute over total mass of solution. Total mass of solution. In other words, if I had a solution, once I've made it, let's say a sugar solution, that weighs 100 grams, and of that 100 grams, if 5 grams of sugar are floating around in there, 5 grams of some solid sugar, what I have is 5 over 100. It's 5% sugar solution. That's what this is. All percentages are just the part over the whole, the part over the whole. Okay, let's do an example. So this is going to be example 2. What is the percent by mass, the percent MM, of the lactic acid solution in the previous example? The lactic acid solution in the previous example. Okay, well, we need, of course, let's do this in red again. We need the mass of the solute. We need the total mass of the solution. Okay. Well, the mass of the lactic acid, so So the mass of the lactic acid, that's just going to be the 7 milliliters times its density. We don't want to go all the way to moles, so we're going to stop with grams, times 1.209 grams per milliliter. And when we do that, we get 8.463 grams. So that's the mass of the lactic acid. So we have our numerator. Now, total mass. Well, total mass. What is our total mass? Well, our total mass is the 8.463 grams of the lactic acid plus the mass of the water. Well, water was 130 milliliters. It gave it to us in volume. Well, the density of water, normally we just take it as 1 gram per milliliter. So 130 milliliters of water weighs 130 grams. So 130 grams. So we have a total of 138.463. And I sure hope that you're confirming my mathematics. I mean, I'm notorious for arithmetic mistakes. Okay, well, there we go. We're done. So the percent by mass of this solution is equal to 8.463 grams divided by, ooh, look at these crazy lines. Can't have that. Tends to happen down at the bottom of the page, so I think what I'm going to do is I'm going to go ahead and move on to the next page because I don't want these crazy lines all over the place. So let's try this again. So percent by mass is equal to 8.463 grams of lactic acid, excuse me, divided by 138.463 grams of solution. And of course, whenever we're dealing with a percent doesn't have a unit. Gram needs to cancel gram. Okay, that's the whole idea. Times 100. And when I do that mathematics, I get 6.11%. So our lactic acid solution was 0.686 moles per liter. It's 6.11% by mass. That means if I had 100 grams of this lactic acid solution, 6.11% of that mass is made up of lactic acid. That's what this means. So 2 ways of expressing concentration. But again, the one that we're going to be concerned with most of the time is going to be molarity, moles per liter. And you already know that from chemistry. Most of the time, concentration, molarity is what we used. Okay. Well, let's see what we've got. So I'm just going to list a couple of the other ways that concentration is expressed, but we're not going to be doing any examples with them because they're not going to be important for our purposes, but I'd like you to know them. Okay. I'll go back to black here. Okay. Some other ways of expressing concentration. And at some point or other, you certainly have heard of these, or you will be hearing about them at some time or other in your career. So one of the ways is something called molality. And molality comes up when we talk about colligative properties, boiling point elevation, freezing point depression. We're not going to be concerned with molality. There's something called mole fraction, very, very important. And again, a fraction is always the same thing. It's the part over the whole. We did percent by mass. There's also something called percent by volume. So it's usually designated as percent VV. I'll just go ahead and write the words out, percent by volume. So if I have 100 milliliters of solution, how many milliliters of that, what volume of that is actually the solute? Percent by mass and percent by volume are 2 different numbers. They're not the same thing. They might happen to be the same thing coincidentally, but they're not the same thing. So, and there are other ways, I'm sure. Okay, let's do another example here. See if we can't combine our concentration things. So, a biochemist finds a bottle that a colleague has left at his bench. That reads L Malik 8.66% mm. Okay. What is this solution's molarity? Molarity. So a biochemist goes to his colleague's bench and he finds this bottle that says L Malik 8.66% mm. So he knows that it's a malic acid solution, 8.66% by mass. He wants to know what the molarity is. What is this solution's molarity? Okay, so in this particular case, we're going to be going from one expression of concentration to another. Okay, so malic acid. I told you that we're going to be dealing with biological molecules, so let me go ahead and draw the structure of malic acid so you see this one. Okay, let's see, shall I do it? That's fine, I'll just do it over here. Okay, so C, 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 C. We have a hydroxy there, and then we have a wedge here. Shall I put, yeah, that's fine, I'll go ahead and put the H's in. And then, of course, we have this. So this is malic acid. It has 4 carbons. It is a dicarboxylic acid. There is a carboxylic acid on one end. There's a carboxylic acid on the other end. And it's also an alpha hydroxy acid because on the alpha carbon to one of the ends, there is a hydroxy. And this wedge just means that it's actually coming out at us. Biological molecules have a handedness. Remember chirality from organic chemistry? So there is an L-malic acid and there is a D-malic acid. In this particular case, it's L-malic, so if we write it like this, it's actually coming out at us. You'll also see it this way, the regular line structure instead of this. It's up to you how you want to draw it, whatever is most comfortable for you. I tend to draw these. I don't really care for these very much, again, because I like to see my carbons. I like to see what I'm working with. Even after all these years, I still just feel more comfortable doing it this way. But of course, in the books, you're going to see it like this. So you certainly need to be able to recognize it. Boom. And OH. So that's the line structure for malic acid. Malic acid is what gives green apples their tartness. Very, very important biological molecule, as you'll find out later in the course when we discuss the citric acid cycle. Okay, so 8.66%. So 8.66% by mass means the following. So they gave us the number, 8.66%. That means this. It means the mass of the malic acid, I'll just call it malic, over the mass of solution, times 100 is equal to 8.66. So they gave us this. This is the definition. So I want to start with this. I'm going to work my way back. Okay, so now let's ask ourselves what it is that we want. Let me do this in red. We want molarity. It's really, really important that you do, that you know what it is that you want. So I want molarity. So molarity, it means I want the moles of malic acid over the total liters of solution. Liters of solution. I need those two numbers. I need this and I need this. How can I get that based on the information that I have? Okay, well, let's take a look at this. So the first thing I'm going to do is I need the moles of malic, liters of solution. The one that's quickest here, what I'm just going to do is I'm going to let me write out what the biochemist did. So the biochemist measures the volume of the solution. Measures the volume of the solution. In other words, he just takes it and pours it into a graduated cylinder to see what the volume is in order to get that number. Measures the volume of solution to be 17.5 mils. So in that bottle, he has 17.5 milliliters. So he has the volume, he has the denominator. Half our problem is done. Now we just need to find the moles of malic acid. Okay, so that's the second part. How do we find the moles of malic acid? Well, I need the moles of malic acid, and I know that I can get the moles of malic acid from the grams of malic acid, from the mass, from the grams of the malic acid. And my conversion factor is the molar mass. Well, molar mass is easy. I just look it up. Okay, so the biochemist measures the mass of the solution. Okay, so the biochemist measures the mass of the solution. He puts it on a scale and he actually measures it. Or actually, he takes a glass vial, he takes its mass, he empties the contents into that vial, and then he takes that mass, he subtracts the mass of the vial that he knows the mass of, and he has the mass of the solution. So the biochemist measures the mass of the solution. Solution to be 17.75 grams. Okay, so now he has the mass of the solution. Well, we need the mass of the malic acid. Well, we just said earlier the mass of malic acid divided by the mass of the solution, the total mass, which is now 17.75 grams, times 100 equals 8.66. We have all these numbers. So now we have this equation. We just do a little bit of algebra to find the mass of malic acid. And that turns out to be actually, let me do it underneath here. Sorry about that. So after a little bit of rearranging and a little bit of algebra, the mass of malic acid happens to be 1.537 grams. Well, there you go. I have 1.537 grams. That's my mass of malic acid. I have my liters of solution, 17.5 mils. Now I just make sure that the units are appropriate. I'm sorry, moles of malic acid. This is my mass of malic acid. I still have to do the conversion to moles. So let's do that. So I've got 1.537 grams of malic times 1 mole. And again, I look it up if the problem doesn't give it to me. 134.09 grams. This is just basic stoichiometry, and I get 0.0115 moles of malic acid. Okay, we are done. So the molarity equals 0.0115 moles of malic acid divided by, and we said we had 17.5 milliliters, right? Okay, 17.5 mils, the unit has to be liters, so move the decimal over 3 times. We over 0.0175 liters, and when we do that, we get 0.66 molarity, or 0.66 moles per liter, my preferred expression for that unit. So that's it. We were given a concentration in one expression, percent by mass. We wanted molarity. We wrote down the definition of molarity, and we just took a look to see what we needed. We needed moles of solute. We needed liters of solution. Well, the liters of solution is easy. You just measure the volume, so that gives you that. We use the information on percent by mass to recover the mass of the solute, the malic acid, and then from the mass, we use molar mass to get to moles. So these are the kinds of things that you want to do. Write it all down. See some sort of a solution path. There's only a handful of definitions. Molarity is moles per liter. Percent by mass is mass of the solute divided by total mass times 100. Everything should come together really, really nicely. Okay, thank you for joining us for our first lesson of biochemistry. We look forward to seeing you again. Take care.